Welcome back to the Explainer. Today we're diving into a family of chemicals that are, well, everywhere. They're in the medicine cabinet, they're in the dentist's office, they're literally in the code that makes you, you. So let's get ready to meet the incredibly important world of amines. All right, let's kick things off with a little bit of a riddle. What on earth could possibly connect your allergy meds, the Novocaine that numbs your mouth, and the very proteins that make up your muscles? I mean, they seem like they're from totally different universes, right? But they're not. They all share one secret ingredient. And that secret ingredient is amines. Yep, that's the one. This single class of compounds is the workhorse behind life-saving adrenaline. It's what makes Benadryl work, it's the magic in Novocaine, and it's even a core part of the proteins and vitamins your body needs to function. They're absolutely everywhere, hiding in plain sight. So yeah, for this first part, we're just going to take a look at how deeply these things are woven into our world. We're not talking about some abstract chemical in a textbook. We're talking about stuff that's working in and around us every single day. Okay, so what is an amine really? Well, the easiest way to think about them is as ammonia's versatile children. You start with that basic ammonia molecule. One nitrogen, three hydrogens. Then you just swap out one or two or even all three of those hydrogens for some kind of carbon group. And that's it. That simple little swap is the secret sauce behind every single amine we've talked about. So, how can one little change make these molecules so incredibly useful? Well, the answer is all in their fundamental structure, their basic blueprint. So let's zoom in and see what makes them tick. If you look at an amine, it's got this cool little pyramid shape, just like its parent, ammonia. But the real star of the show, the thing that gives it all its power, is that unshared pair of electrons, just sitting on top of the nitrogen. This lone pair, as chemists call it, is the source of pretty much all of their reactivity. It's their secret weapon. Now check this out. In a perfect world, in a perfect symmetrical shape, you'd expect the bonds to be about 109.5 degrees apart. But with amines, it's a little squished, down to about 108 degrees. And why is that? Well, it's because that lone pair of electrons we just talked about is a little pushy. It takes up more space and shoves the other bonds just a little bit closer together. And this brings us to how we sort them, which is actually super straightforward. It all just comes down to counting. How many of those original hydrogens on the ammonia did we swap out? If you swapped out one, you've got a primary amine. If you swapped out two, it's secondary. And if you replaced all three, well, you guessed it. That's a tertiary amine. Simple as that. Okay, so we know what they look like and we know how to sort them into their little families. But how do scientists actually make them in the lab? Let's check out one really clever, really important method. Now, this method is called the Hoffmann Bromamide degradation reaction, and it has this really fascinating, almost counterintuitive twist. As our source material puts it, the amine so formed contains one carbon less than that present in the amide. Did you catch that? In this reaction, you actually lose a carbon atom along the way. So here's the play-by-play. You start with a slightly different molecule called an amide. You mix it up with some bromine and sodium hydroxide, and through some chemical magic, a specific piece of that molecule, the part with the carbon and oxygen, just gets plucked right out. What you're left with is a primary amine that's exactly one carbon shorter than what you started with. It's an amazing tool for when you need to precisely shorten a molecule. All right, let's get into the personality of these molecules. Let's talk about their reactivity. What is it about their structure that makes them so useful, so ready to jump into chemical reactions? Really, it all boils down to a couple of key things. First, remember that lone pair of electrons? Well, it makes amines basic, meaning they can grab onto protons. It also makes them nucleophilic, which is just a fancy way of saying they are drawn to positive charges and are really eager to get reactions started. And second, the number of hydrogens still attached to that nitrogen makes a huge difference, which is why primary, secondary, and tertiary amines all have their own unique personalities in a reaction. And we can actually use those different personalities to our advantage. There's a classic lab procedure called the Hinsberg test. It's a fantastic bit of chemical detective work. You add a special chemical, and you can tell exactly what kind of amine you have based on what happens. The primary amine reacts, and its product dissolves. The secondary one reacts, but its product doesn't dissolve. And the tertiary amine, it just sits there and does nothing at all. Pretty neat, right? Now, as useful as amines are by themselves, they're also the key to unlocking an even more powerful chemical tool. This is where the world of amine chemistry gets really, really exciting. We're talking about diazonium salts. You make them by taking a primary aromatic amine and reacting it with nitrous acid. But, and this is important, you have to do it at really cold temperatures, right around freezing. They tend to be pretty unstable, but believe it or not, that instability is exactly what makes them so incredibly powerful. So you shouldn't think of a diazonium salt as the end of the road. It's not a final product. No, you should think of it as the ultimate chemical gateway. It's like a master key in organic chemistry that lets scientists open up doors to hundreds of other compounds that would be super difficult or even impossible to make any other way. So here's the magic. The diazonium salt has a piece with 2 nitrogen atoms, the N2 group. And this group is what chemists call an excellent leaving group. Basically, it loves to pop off the molecule and float away as super stable nitrogen gas. And when it leaves, it opens up a spot for all sorts of other things to jump on. Things like chlorine, bromine, iodine, you name it. It makes tricky chemical substitutions suddenly become easy. So, when you put it all together, amines really play 2 incredible roles. On one hand, they are nature's essential building blocks, fundamental to life itself. And on the other, they are a chemist's master key, unlocking the ability to create countless other molecules. Which really just leaves us with one big question. What incredible problem are they going to help us solve next?